some of the energies that are really important in a thermodynamics problem are these big energies of heat transfer and work transfer and mass flow rate that adds additional energy transfer. So the mass could be hot, or the mass could do work itself. And the energy balance then, if we say, E out equals E in, for example, or we can say that we can bring that over to one side of the equation. Delta E of our whole system is going to be E in minus E out. Then we can recognize that some of the energies in the system are due to thermal. So that's going to be, I'm going to write it just in a different way because it's already written here in one way. I'm just going to write it in a different way. E in equals E out. I'm going to go E in equals E out. And the way I like to always think about this is there's going to be some heat on one side or the other. There's going to be some work on one side or the other. There's going to be some energy due to this mass flow rate, on one side or another. The sum of all of them on one side has to equal the sum of all of them on the other side. So all of the in has to equal out, out, out. I like looking at the equation like this better, but some people like looking at it like this. So this is really a great starting point for any first law energy balance questions. And then you say, oh, well, in this question, heat is leaving the system and no heat is being added, so that goes to 0. Or in this system, we don't do any work from the system to the surroundings, so that equals 0. So you start with this equation and then you go and you turn a lot of these terms to 0. But by all means, always write every single one of them when you are doing a first law energy balance that involves heat transfer, work transfer, and mass flow rate. That's an open system.